As the director of the Institute of Advanced Studies, I'm very, very pleased to be welcoming Professor Younis today to speak to us and give us a discussion of some of his most recent work. And we are very delighted to host Professor Younis, also because we have waited quite some time to host Professor Younis, whose initial plan to visit us was disrupted by COVID, and this is our second attempt. And as we mentioned upon his arrival, this is also a really nice visit in the sense that it is a deepening relationship between the university and colleagues here at Loughborough, and colleagues as well at KAUST, and colleagues, and I'm very much hopeful, extending now also to SUNY. So we have now a very broad-based relationship across the institutions in relation to this fellowship. And so we are thrilled to be able at last to welcome you to the Institute of Advanced Studies. For those colleagues who are joining us online, as I've said, please do feel free to get involved in the dialogue and conversation through the chat or through the Q&A, and we will make sure that there is conversation that way, and we pick it up. And for those in the room, we will also, of course, have a chance to have some conversation and some dialogue after the paper. At this stage, I'm going to turn over very much to my lovely colleague on my side, Amal Azej, who is going to do a more formal introduction of Professor Younis for this webinar. Thank you.
Yeah, thank you, Marcia. So we are honored today to have Professor Younis with us to give us an interesting presentation. So Professor Younis, he received his degree in engineering mechanics from Virginia Polytechnic Institute in 2004. And then he served as an assistant and then associate professor from 2004 to 2013. Of mechanical engineering at the State University of New York, SUNY at Binghamton. And since 2013, he moved to King Abdullah University of Science and Technology in Saudi Arabia, where he served as an associate and then a full professor of mechanical engineering, and also the director of MEMS and NEMS characterization motion laboratory, to whom I belonged during my PhD. And in 2021, he moved back to SUNY Binghamton, where he serves as the professor of mechanical engineering. So Professor Younis holds several US patents in MEMS sensors and actuators, and also he has more than 10,000 citations. And also he has one of the famous book in MEMS nonlinear dynamics, and the book name is MEMS linear and nonlinear static and dynamics. He graduated around 20 PhD students, and I am honored to be one of them. So Professor Younis today, he will present for us an interesting presentation about undergoing dynamic-based micro and nano devices and phenomena. So the floor is yours.
Thank you very much, Amal. Thank you, Marcia. Thank you, everyone, for hosting me. Also, Stefanos, I appreciate the hospitality. You guys are the host, and I'm very honored and humbled by the nice words, and extremely happy finally to make it after a couple of years of delays. So thank you very much. It's really an honor to be in this great institute, and also being hosted by my superstar Amal Hajjaj, one of the best students I met. So thank you again for this opportunity. So as the introduction said, I'm honored to be affiliated with two great universities, KAUST in Saudi Arabia and SUNY at Binghamton. Both are interestingly located in very interesting places. So let's talk geography. So this is upstate New York. They show you green, but in reality, most of the time what we see is white. It's a very beautiful campus in upstate New York, not so far from the borders of Pennsylvania. If you see the cursor, I guess you see that Binghamton is located here, and this is the border separating New York from Pennsylvania. And this is the circle shows where we are in the map. We are more or less 3.5 hours away from the big city. So this is more of suburb campus. And KAUST shows the beautiful pictures, and it's on the Red Sea, located almost near the border between, if you extend the line between Egypt and Sudan, you hit Peninsula, Arabian Peninsula. This is where almost KAUST is located. So it's where you see the red circle. And today, most of my research actually has been done at KAUST. So I acknowledge their support in what I will present today. So let's talk about the technological needs. I think we live in the world of lots of data, basically. So especially with the so-called Internet of Things have made the spread of data everywhere. We use lots of data coming from cheap sensor nodes because it's no longer expensive to have sensors. So these sensors are deployed everywhere and they send a huge amount of data. And that actually created a couple of problems. First problem is the energy cost, because the transmission of data does not come cheap. It really costs money to wirelessly transmit data. And the second problem, how do you translate this data into information or knowledge? So you really need to process the data, and you need a bit of computing. And most of the time we rely on microcontrollers to process the data and transfer it into useful knowledge. So whether it's computing or transmission of data, that means huge power consumptions, and also the data itself, how to translate it into knowledge, created also a problem. So what is the potential solution? So I mean, you can use machine learning to translate these data into knowledge, and that's why this business of artificial intelligence and AI evolved recently, aiming to deal with this problem. But still, the energy problem is not solved, because machine learning means computations, and that does not come with no price. And we live nowadays with the crisis of energy. So really, it's a fundamental question how to do things efficiently with minimal amount of energy. So my proposed solution, I think, is to increase the intelligence at the device level, meaning you don't really need to send all amount or all kind of random data. Instead, why don't you select certain data of useful information and you care about transmitting them? And to do that, you really need to increase the intelligence at the device level. So the device level at the sensor node needs to be smart, selective, multifunctional. And then this way you reduce the amount of data you have to worry about and the amount of data you need to process. And in my point of view, devices at the micro and nano devices at the micro and nano scale are ideal platform to do that. They by themselves are energy efficient devices, and they have the ability to do things in a smart way. So I do research from the angle of dynamics and mechanics. And from my little experience on this field, I can tell you there are lots of exciting opportunities where you can make use of motion at the micro and nano scale to achieve things that very hard, if not impossible, to achieve on another scale. So that's the journey that I want to discuss with you, my attempts on this side of the technology. So in this talk, I will feature a few case studies. I will try to speak about them briefly to kind of just intrigue you and encourage further research and discussions about some of these ideas. So the ideas I will present by no means are ready for commercializations or fully developed. I'll just touch base on these and overview their principles quickly with the hope to motivate further deeper research into these topics. So let's talk about bifurcation-based sensors and switches. So for people who know dynamics, you know that the natural frequency is the square root of K over M, stiffness over mass. And people at the microscale technology realize that if I monitor the natural frequency of a structure, then I can tell if it catches a mass or sniffs a gas or catches a bacteria or viruses by comparing the original natural frequency of the system, like what you see in black here, and compare it to what happens after it catches this mass. So that creates this shift, and that translates into a frequency shift, which is proportional to the amount of mass that is being caught, whether it's a gas concentration or a virus or a bacteria. So this presents the principle of or the classical principle of operation for a mass sensor or a gas detection system at the microscale. So this is in the linear sense. I do dynamics in the nonlinear sense. So I will try to show you a spin out of this idea. So for that, we fabricated a microstructure made of silicon. We can see it in the schematic. We functionalize it with a polymer that is sensitive to humidity or sensitive to volatile organic frameworks. So basically certain gas. And we had a proper setup for watching the motion using a laser Doppler vibrometer, and the setup to allow the gas to enter an environmental chamber at certain concentration. So without much details, this is the setup. And this is the nonlinear response of that structure, because this structure is actuated by electrostatic force, which is kind of induces nonlinearities on the system. So instead of having the typical linear frequency response curve, we obtained this strange curve, which looks nonlinear with jumps. And the basic idea was, if you want to increase intelligence, then maybe we can think about combining sensing with maybe alarming or another functionality. Meaning, if I'm, for example, as a sensor, we are observing the concentrations of CO2, then at certain level, CO2 becomes dangerous. Then I want to realize an alarming switch or an actuator that can tell people, you know, this is a dangerous situation, exit the room, for example. So from a dynamics point of view, you can think about this curve as the following. If I operate at this vertical line, then as the beam catches gas, then the frequency, natural frequency, will shift backward. Or equivalently, you can think about climbing this curve. So at zero mass, you are at amplitude A1. And then with a bit of mass, you are at amplitude A2, and so on. And then at A3, what happens? There is a sudden jump in the amplitude from A3 to this point. And then we thought, okay, this jump can indicate exceeding certain threshold, safety threshold. Then my students said, okay, why don't we have a program using a microcontroller to tell that if you exceed A3 as an amplitude, then you can trigger a LED or an alarming signal to indicate that this is a dangerous level. So this is what we call switch triggered by the presence of gas. And you know, the concept was demonstrated with a LED light and so on. So when I looked at this, I said, that's fine, but we use the microcontroller. That's not the point of what we are saying. We want to get rid of computing and rely on the dynamics itself. So for that, I can borrow a concept from nonlinear dynamics. So the question, can we do this switch without a controller? So the people who know dynamics, there is the so-called single potential well systems. You have a ball that can vibrate back and forth if it has certain energy, but if the energy exceeds certain threshold, actually the ball can swing and escape the potential well. It's called the phenomenon of escape, basically. And it's a characteristics for systems with a quadratic nonlinearity, like the systems that I'm dealing with. NEMS, they are actuated by electrostatic force. They have this kind of nonlinearities. So long story short, there is a band in these systems. You see them in the gray, where the ball has to escape. And if I'm talking about a vibrating structure, the vibrating structure has to collapse if I'm operating within this band. So this characteristic curve shows forcing versus frequency. Anytime the operating point within this band means that what's supposed to vibrate, it will collapse. So I want to make sure to make use of this phenomenon. These are a few experimental data on MEMS devices showing frequency response curves with those bands opening. These indicate bands of frequency where the structure will collapse like a switch. And this is another way, experimental curve of the instability tongue, you can call it, where if the structure is operated within this band, it will force to go down. So the idea when it goes down, I want to have a proper electric circuit to realize a switch. And then I can program these things to happen when the gas concentration exceeds certain threshold. So this is kind of the experimental realization of the idea. And you can see the experimentally obtained frequency response curve. You see the opening, the instability band. So this is the initial operating point of my system. We tested experimentally before the exposure of any mass for some time to make sure that we have a stable operation, meaning I don't have instability because of noise or because of disturbances. Now I'm going to expose this structure to gas and hope that the operating point will lie within the instability band as the structure catches more of gas. So this is what you will see now. You'll see animation showing the instability creations and then the collapse when the mass exceeded a threshold that usually of interest to us. So this is, I thought, a nice idea because I did not use a microcontroller. I did not use anything. It's just the dynamics of the device. So we wanted to upgrade this idea more. Some other challenges in this technology, the temperature sensitivity. So can I also account for variations of the response of the system when the environmental temperature changes? The state of the art, usually what they do, they build two identical sensors. One of them you can expose to the gas or whatever you want to measure. The other one, you shield it from that thing. And then both will be affected by temperature variations. And then basically you take the response of one, subtract it from the other, so that you eliminate the temperature effect on your sensor that might lead to erroneous predictions. In our case, we thought we don't want to complicate things with two devices. Can I use the same device, but two modes of vibrations? For people who are in this business, they know that structures, they have infinite amount of modes, and the first few of them are actually dominant. So for example, here I show you I guess the first mode and second mode, and I want to operate my system such that I can monitor the frequency shift of these two modes of vibrations, and so that I can catch two quantities of interest. One of them is temperature, and the other one would be, for example, gas. So two unknowns, two equations, and you know, the problem of temperature effect will be solved. So this is my objective here. So this is the case study, same structure, and you know, half electrode to excite the antisymmetric mode. And basically, these are the characteristic curves showing how the frequency changes when you increase the concentration of the gas or when you change the temperature. And you know, there are two ways to present the data. And down, they are, you know, concentration on the x-axis, and up it's the time. Anyway, so we characterize the system for various temperatures and various concentrations. Then we basically took a case study. So if I measure the first natural frequency of the system to be 118 kilohertz, the second one 290. Can I tell what would be the temperature and the concentration of the gas? And when you look at these black curves, their intersection, they will intersect with various curves, but only one of them satisfies or makes perfect intersection with the horizontal curve, which is a temperature of 45 Celsius and the concentration of 1750. So this is, in short, a demonstration for this kind of multifunctionality sensors, or increasing the level of smartness that I'm promoting. And maybe you can combine this with a switch, actually. I did not do it here, but it can be done. So you can have a switch and the sensor and the temperature compensation. In fact, in this slide, what we did, we realized a switch, and at the same time used the higher order mode to record how much mass is being detected. Because higher order modes, they have sensitivity that are more than the first mode. So it's like having two separate sensors. One of them is really sensitive for mass, that's the higher order mode, and the other one is supposed just to do the switching. So this is the experimental realization of this. Of course, here you have to have two simultaneous excitations, and then as you first you make sure that things are stable, and then as you expose the mass, you have switching of the first mode, and you have measured frequency shift of the second mode for people who are interested in this. So this is kind of one of these projects that we thought we can make the functionalities a bit more sophisticated and reduce the transmission of data. Now I'm going to shift gear and talk about other family of sensors based on a different principle. So far, what I demonstrated was relying on a structure that you coat with polymers or with functionalizations. The other research, and we started this with Amal here, that why don't we make use of the cooling or heating of a structure, how much it can be heated or cooled when it's exposed to gases or various even air pressure. So the first basic concept, and again, you see Amal was the one who started this, is to realize a pressure sensor based on the cooling of a wire, basically. So if you pass a current through this beam, then there will be joules heating. And then by exposing the structure to air, there will be cooling for this structure. And you know, the structure, if it's heated, then there will be axial load. And in a sense, you are modulating its resonance frequency, or you are affecting its stiffness. So if you measure the natural frequency and you start to play with the pressure inside, then you are indirectly affecting the stiffness of the structure. And hence, the more pressure you add, the more the resonance frequency of the structure will be affected. So in a sense, you can realize a pressure sensor. So in this case, more pressure means more air cooling the structure, less axial force, and hence, the more you add pressure, the more the frequency will shift to the right, and you can calibrate this to realize this kind of a pressure sensor. I mean, why this is attractive? Because you don't need a diaphragm or complicated designs. You can make this as small as a carbon nanotube if you want. So it's really a sensor with no headache of big structures. All right, so I think these results were attractive, but not so attractive, because the frequency shift was not big, from 50 to 43. Sensitivity is not, it's good, but it's not big. And second, the range was not big. I only, you know, we were measuring from almost 0 to 25 torque. So to deal with the sensitivity issue, we resorted to the buckled structures. People who deal with structural mechanics knows that if you buckle a beam, then near the buckling regime, it becomes very sensitive to the variation in axial force. So that's the basic idea. You see here how the frequency of this structure goes down from 60 to almost 0 near the buckling regime as I increase the electrothermal load, which is the axial load, the compressive load. And then this is the post-buckling behavior. So that's what we want to do. We want to operate at near the buckling regime, expose the structure with pressure, and see how it's going to go. So as we expose it to air, then the frequency, the resonance frequency will change, and then you have a considerable shift from near 0 to whatever number. That's more than hundreds of percents of shift in frequency. So again, these are the work of Amal, and you can see here that the frequency has shifted almost 120%. In one case, the other operating point showed me almost 80% of shift, and hence you have a highly sensitive pressure sensor. Now, if you can see on the x-axis, the pressure range is still not that much, and that's a technological problem. We want to extend the pressure range beyond 10 torr, hopefully to atmospheric. So how do we do that? So in this case, I had to resort to another dynamical phenomenon, which is called veering. In veering, what happens, you have two modes of vibrations. As you tweak a parameter of a bifurcation parameter, in this case, it's the electrothermal voltage, their frequency get close to each other, and then they get hybridized as mode shapes and basically affect each other in some way. So the idea, I want actually my pressure sensor to operate in this mode in blue. And then as I increase the pressure, and then when I reach a stage where this mode plateaus, no longer sensitive to pressure, I'm going to switch my attention to the other mode in red. And hopefully this way I get to enjoy a big range of pressure variations, and I get to realize more, a pressure sensor with a wide range. So this is the idea. This is, I think, schematic showing what I want to do. We will be operating at this point and then keep tracking the frequency shift of those two modes. Sometimes the upper one will matter, sometimes the lower one would matter. In total, you get a highly, a high range pressure sensor. And this is the experimental data showing going almost from atmospheric all the way to the very low pressure range, using these two modes of vibrations. So this is, again, hopefully it's of course these ideas are not totally mature, but hopefully they inspire thinking about these dynamical features, how we can use them for practical applications. All right, so back to the gas sensor approach. So if pressure can changes the rating of cooling and heating on the structure, then also if I fix the pressure and change the gas type, then also I might end up with changing of the heating and cooling on that structure, and maybe I can get some kind of a gas sensor, right? So and hence we looked with Amal to this problem, and we realized that gases can be classified into at least two categories. One of a thermal conductivity higher than air, which you see it in the left. And hence you can think about those that if I replace air with this category, then I will get more cooling effect, right? On the other hand, the other category in red, if I replace the gas in the chamber, the air in the chamber with this category, then there will be less cooling, and hence the structure will heat up. But the problem, if I monitor the frequency shift, so if I'm operating at this vertical line and I'm only looking at mode number 1, then whether I go right or left, I will only see increase in the frequency, in the frequency, resonance frequency, if I only monitor the resonance frequency. So how do I distinguish which category of gases I'm dealing with? And I get the bright ideas came probably from Amal that let's look at the second mode of vibration, because it has a signature that we don't see it in the first mode. Because to the right of this curve, we see the resonance frequency of the second mode plateaus and is no longer affected by the increase in the axial load, whereas to the left it increases. So the idea was, let's look at the two modes, and this way you not only you get quantity or frequency shift of what you are capturing, but also you can classify which category of gases you are dealing with. So in a sense, it's let's say not a complete selective gas sensor, but at least it gives you classification. So I guess this is the animation for both categories. If it's from this side, that's how the shift of frequency will be. And from the other category, it will be shift to the other side. So these are some data from the first category, the cooling. You see the animation, we're shifting to the left. And hence, when you look at the first and second resonance frequency, you see both are increasing. So delta F2 is an indication that which category we are. And delta F1 is capturing accurately the mass that is being detected. Also, we are comparing with the classical approach of resistive change, because the state of the art, they don't rely on frequency shift, but rather rely on change in resistance. And you can see there's a huge difference. We are talking about 0.4% compared to what we recorded, which is almost 120%, 160%. So it's very sensitive gas detection principle, and it's based again on dynamics and principles of dynamics. This is the second category, which shifts to the right? So here the shift will be to the right. And you can see delta F2 is almost flat. So now I have the classification of what gases I'm dealing with, and delta F1 gives you kind of the amount of mass you are catching. All right, so, and then we thought that, can I make use of this thermal conductivity devices to be completely selective? In this case, we said, okay, let's use machine learning. And machine learning is not new. It's not a new idea. People have used it for chemoresistive sensors, or sensors that are based on resistive changes. And we wanted to do that based on this thermal conductivity sensors. So this is an overview of the approach. It's just standard things. You collect data, you acquire them with data acquisition. You get the response of the sensor as a raw data, how it responds, whether it's a frequency or amplitude versus time. But you collect several of these experiments because you will use them for training. So we collect the data for various kinds of gases. And then we do what we call feature or signature extractions, you know, maximum, minimum, and stuff like that. And then we kind of reduce these features using what we call principal component analysis. It's a way to reduce these data from being in the hundreds to very few. And hopefully the PCA will tell you the signature mark for every gas type and for every concentration. This is what we are after. But if you want to do it automatically, then you need these classifiers, the neural network, the k-nearest neighborhood, and so on, so that it's automatically done, not by visual inspection. So this is in short what we want to do. In this case, I'm going to show you amplitude because I'm going to operate at a fixed frequency and, you know, expose the structure to gases. Some of them will shift the frequency to the left, to the right. It doesn't really matter. I'm going to record the amplitude, how it behaves with time for various gases. In this case, 3 gases and with 3 concentrations. We will, of course, hide some of the data from the classifier so that what we call validate. We show the classifier a new data that was never shown before. So a bit of technical details on this. But anyway, we record the data. We do feature extractions. The students, Wagner here, did a great job with Osman. I mean, there are 2 ways to extract features. One of them from a module in Python. And again, I'm not an expert on this, honestly. The students did all of this. I don't know Python even, but they have these features in which you can extract gazillions of features. In their case, they extracted literally 700 features out of this signal. That's a lot. I mean, in my head, it's going to be maximum and minimum and area under the curve, but they extracted 700 features. And then they looked into another, what they call personalized or customized approach. They were curve fitting the rise up and rise down of the curve, and they came up with 32 features. So one approach 700, the other one 32. Still a lot. And then these features, unfortunately, many of them are dependent on each other. They are not independent. And the systematic way of looking at this is to look into what they call the correlation matrix or the heat map. And long story short, if you see red color here, this means this feature is not independent from another feature. For example, I don't know if you see the cursor. This red means this feature X is the same as almost feature Y. So lots of redundancy in the data. So they do this test and classify what is independent and what is not independent and drop this redundancy. Anything with red will be dropped. And they ended up with 19 out of the 700, only 19 feature. And from the personalized data, out of 32, they ended up with 7. So it's reasonable. The next step in reduction is to project these parameters. All these parameters will be projected into very few. They will take the eigenvalue of the correlation matrix. And this is technical term, but what it does, it's a way to project all of these parameters into very few, 2 or 3. Very nice technique, right? Mathematically, it's an eigenvalue problem, etc. So the idea that if I can project these eigenvalues, they are called PCA1, PCA2, PCA3, then probably, as I can show here, results from the literature, you will start to see gases fitting in certain regime of this space and other gases fitting in another regime. So you get a really unique signature and pattern detection out of these. So the question, can we do it with our data? So this is the 3D projection and the 2D projection for our data. And in short, if you get dizzy by this 3D animation, but you can see cluster of data uniquely positioned along these curves. Some data will be here with certain concentration, another gas will be in red with certain concentration, and so on. So visually, you get a bit of feeling of what's going on. It seems this method successful, right? Of projecting the data in various domains. And then we did it in a more systematic way using quadratic discriminant and KNN and so on, which is a way just to allocate that this thing belongs to this gas and this thing belongs to this concentration. And basically this matrix shows that we have a 100% accuracy. That was fun. You know, everyone is doing machine learning, so that was fun. But machine learning is a pain. Again, I don't like processing a lot. So still, it's an open question. I want to eliminate machine learning. What we achieved here, we just demonstrated that we can get something out of these conductivity-based sensors. But still, In this case, to be selective completely, we needed machine learning. I'm going to show you another attempt of not doing machine learning and hopefully improve selectivity of sensors, again based on dynamics. So, and the dynamics here is even linear, it's not nonlinear. It's just looking at two different modes. So in this case, we resorted to this structure. It looks funny. It's like a structure, a beam, and attached to it a T-shaped structure. And then from the dynamics, we noticed the following. We noticed two distinct modes of vibrations. One in which this T part goes up and down significantly. That's the first mode. And the second mode, it's probably dominated by the motion of this beam, not so much the motion of that T structure. So again, the idea, can I make use of each mode to be selective to a different gas? So the way to do it, we decided to coat this big structure with graphene oxide, which is selective to, say, for example, humidity, or can be selective to whatever you want, CO2. Anyway, so we coated this T shape with graphene oxide so that if I operate at this mass mode, only this mode will be affected by the presence of humidity, for example, not this mode. On the other hand, this mode, which depends on a beam, I want to use the thermal conductivity idea that I talked about. So honestly, I like this work because it combined what I presented so far, thermal conductivity and absorption-based sensors. And the question, can we do them, the two independent? I guess the case studies will be what? Helium and probably humidity. So this is the experimental technique. Long story short, it's magnetic and electrothermal actuation, Lorentz force to get this thing vibrating. This is the gas setup, standard procedure of microcontrollers and so on. I'm sorry, mass flow meters and so on. And these are the results. So when I exposed the structure and looked at this mode, what we call the mass mode, to humidity, we noticed considerable shift in the amplitude from 45 almost to 20. But when I exposed this mode to helium, that the amplitude did not change much, from 48 almost to 42. So clearly this mode is very selective to humidity and not so much selective to helium. Vice versa. Let's expose this structure, which is a thermal conductivity based sensor, to both gases and see. When it was exposed to helium, actually it showed considerable shift in amplitude from 98 to 133. But when we exposed it to humidity, it did not care much, almost constant, right? So a very promising approach, shows, some level of selectivity by playing with the modes and having, different principles of sensing and different modes of vibrations at your service. All right, so this is the first part of my lecture. I think I have like 15 minutes or so. The second 15 minutes will not be practical. So this is fundamental. And for people who love dynamics and math, this is your second part now. And that actually exemplifies my research. It's literally two parts. Part that is theory and for the math geeks, and the other part is practical and for people who don't care about math, care about applications. Internal resonance, this research also started with Amal Hajjaj here. We did some nice work over the years showing how different modes of vibration interact and speak to each other. And this is something that is not, you don't show it because you like it. It is there. It was reported numerously in the literature. And at the start of the technology, people did not even understand what they are seeing. Why these different modes talk to each other and affect each other. So it is something numerously observed at the micro and nano scale. So I will go briefly over what we did with Amal, and then I will show more new results on this. I guess this is the theme of my presentation today. I start from where Amal stopped, and then I continue to show you where we are now. So the fact that we can tune the stiffness of the arch by passing a current was very useful, because in a sense you can play with the stiffness and play with the frequencies. So basically what you see here are the first natural frequency of an arch curved structure, right? And I show here why we care for curved structures, because they are stiff. And we will actuate them with electrothermal actuation, like what I said before. So this is how the frequency of these structures change with the electrothermal voltage. And basically, you can play with the ratio between the first natural frequency and the second natural frequency. If you look to the right, you see the ratio goes sometimes near 3, near 2, sometimes near 1. And in the bottom, you see going from 4 almost to near 1, passing through 3 and 2. And one recipe for the modes to interact is to have a ratio between the modes frequencies 3 to 1 or 2 to 1. This is one recipe. The other necessary condition is to have the proper nonlinearities, which is quadratic and cubic in this case. So without much details, we succeeded of demonstrating this 3 to 1 internal resonance and 2 to 1 internal resonance on this arch. Basically, if you look at the spectrum of the response outside this internal resonance, you only see a spike corresponding to the mode we are exciting. And within this funny shape, which plateaus, you start to see 2 spikes, which is a kind of a nice quantitative measure or indication that you have 2 modes are interacting and exchanging energy with each other. And that's in agreement with what we observe from perturbation techniques and analytical techniques, where you see mode in red emerging while the other mode in black, kind of saturates and so on. They exchange energy. I guess Amal showed different results over the years for 1 to 1 and 2 to 1 internal resonance. Very interesting results here, and were verified using Galerkin and multiple scales. I'm not going to talk about it in details here. And also, Amal was intrigued by showing chaotic behavior. So she showed it experimentally and theoretically. So these are a few clips showing the potential of getting very complex behavior out of this system. So this is these videos showing, erratic behavior, sometimes very high frequency, sometimes very low frequency. And sure enough, using, the analytical techniques, she showed that you get all sorts of complexity in the dynamics and strange attractors and so on. I guess for the interest of time, I will jump to the, without much details, to the final case study of today's topic, where we demonstrated internal resonance on this interesting structure. This is a U-shaped structure. So if you can see, looks like a U. And it's going to vibrate in plane. So in the plane of this slide. And we will actuate it with electrostatic force and see how we can maybe look into internal resonance in this structure. So we will dub this columns, and the middle one we'll call it coupler. So we will have 2 electrodes to actuate the structure. Today, I'm going to show results for the actuation from electrode 2, meaning I will put voltage load on this structure and it will start to vibrate in this direction. I'm avoiding using the laser because the cursor gives me more, smoother way to flip between slides. The pointer is a headache. But I hope it's clear that electrode 2 will be used to actuate the structure with the electrostatic force. This is a simple model developed by postdoc Rodrigo, and it was developed based on Rayleigh-Ritz or finite element approach. So it's a 2 degree of freedom. In the first mode, Q1 represents the motion horizontally, so it's like mode 1, and in Q2 represents the motion out of plane. Long story short, the 2 equations are nonlinear, and they are coupled, and they show all sorts of quadratic and cubic nonlinearities, in addition to the electrostatic force, which itself is a big source of nonlinearity. The experimental setup we will use here a stroboscopic camera, because in-plane structures, are hard to be caught with a laser, but with a high-speed camera, you have a better chance. So these are the experimental modes. If you look to those 2 videos, it shows the sway mode when the columns move right and left. That's mode number 1. And when basically the coupler moves up and right, that's mode number 2. And now what we are after is to see if we can make these modes exchange energy, exchange rules. All right. first trick we do, we play with the electrostatic force so that we achieve a ratio of 2 to 1 with the natural frequencies, because this is a recipe, this is a must for this energy exchange. So this is the operating point that we choose, where the ratio is exactly 2 to 1. And basically, this is the response in the absence of any funny internal resonance. It's just frequency response curve, linear, nonlinear, but nothing beyond. Now, I want to operate near the internal resonance. And because the camera can can be synchronized with one frequency only, that actually played nice role, because we can synchronize it with mode number 1 and then record the sway mode, which is in magenta here. Or I'm sorry, the other mode. This is the second mode. The first mode is in black. So if I synchronize the camera with the first mode, it will show me the black. Second mode, it will show me the magenta. This is classical internal resonance, and it's very interesting. I guess here some of these videos showing basically when the mode was synchronized with the first mode. I want you to keep in your mind that I'm exciting the system near the second mode. And I'm not supposed to show actually any horizontal motion, right? The only reason why I'm seeing you are seeing in the video a horizontal motion is because of the internal resonance. So it's just a different way to see the motion. This is when it's synchronized with the second mode. There is a motion in the second mode, but you can see blurry motion of the first mode. The camera is not perfectly synchronized with that column, but still you can recognize there is something going on there. So these are, cool videos to show. This is more quantitative ways to see things. Compared with the numerical simulation, the agreement is good. Now, I encourage my postdoc to get this classical saturation phenomenon. It's a nicer way to show results, and it's in line with what was reported in the classic literature, which is that you have a mode in black, you put a force, and the mode is sleeping. So you see there is no response in black here, right? Only you see response in red triangles. You increase the force, and the response increases. And this is life. You put X power, you get Y response. You get 2X power, you get 2Y response. That's what you see in the red. Until this point. And then after this point, this is where it becomes interesting. You start to put power, and the mode is just flat. Does not want to do anything. Whether you put 10 volt, 20 volt, it doesn't really matter. It does not want to move. Why? Because there is another mode that started to steal the energy, basically. You see the black, all of a sudden, although, and again, this is what we need to keep in mind. I am not exciting this mode in black. I am not getting close to it. I'm putting energy to the red. Literally, the black came and started to steal the energy and going up. Very exciting, by the way. I wish I am the first person to report this. I wish I would win a Nobel Prize on this. But that was reported 50 years ago by my advisor, literally 50 years ago. See the classic curves? He demonstrated this with multiple scales analytically. And he could explain what was reported by ships and phenomena that was reported more than 150 years ago by Faraday and those people. They reported this and they could not explain it. So my late advisor, he could explain it using math. That was astonishing in my point of view. So yeah, I'm faking it. I'm imitating him. Nothing new here, but I guess the application is new. And then my postdoc did a nice animation here for how the energy transfers from what you excite to what you don't excite. If you wait, you will start to see more motion in the horizontal direction. So this is based on his equations that he developed. So it's very nice. You can see significant motion to the side and how the motion transferred from up to down. I guess that's very nice visual way of doing things. Okay, so this is, I guess, experiment and numerics and multiple scales, they all in agreement. But I want to end up with a nice slide that summarizes many of what I'm reporting today. So yeah, this is just saying that theory and experiments are in agreement. So this is an elaborate numerical results that he did. Really, I give him the credit. So what you see on this vertical line is the DC load. The DC load, what it does, it changes the ratio of the frequencies. So instead of being 1 to 2, it might be 1.9 to 1, or 1.95 to 1, or 2.1 to 1. That's called tuning. So to the left is the mechanism to do that. And these are examples in this row, figure C, D, E. So for example, 1 DC gave me figure A. The frequency ratio is greater than 2. And if you observe what we see, mode number 2, the magenta, is almost dead, right, in that frequency range. And mode number 1 in black gets awake here and then dies back there. You can see this in this colorful diagram. Looks confusing, but I'll try my best to explain it. So this is what you see on curve A. If you move horizontally, you see black, 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 right? And then for a certain band, there is large motion in red, and then black. And this is mode number 1, horizontal motion. So the black here corresponds to this figure, whereas the magenta there corresponds to the second figure to the right. So if you look at curve A, you see nothing, right? There is nothing, there is no light. So there's no energy in that mode, and that's what you see in the magenta. And so on. Curve, for example, figure D here, you will see in this case B, you will see the first mode is active over a wider range. And that's what you see here. And you see for the second mode, it's active a little bit, nothing, and then active. And that's what you see in the magenta. Active a little bit, and then goes back to 0, and active to the right. What is intriguing to me when I saw this, what is intriguing, the fact that if you see this colorful shape, it looks very much like this black shape. As if I took this color from here, as if literally with a Photoshop, I took this cut and put it paste here. And that's a true meaning for stealing energy, right? Literally, this mode got all of its energy from this mode. And you can see the similarities in shape. It's astonishing the way it's too good to be true, honestly. And surprisingly, I guess this paper took a year in review. I don't know why, but one of the reviewer seems having fun. So he started to throw all sorts of questions and hard things. So he asked him to do this experimentally. And surely enough, after a few months of hard work, he did it experimentally. And you can see the attempt to generate same things based on experimental data. And it's astonishing the way that you see the energy exchange between these two modes. I believe I am at the end of my lecture. So this is the conclusion that I hope I showed you intriguing and complex phenomena that are worthy. Some of them, they have direct applications for devices, and others, they are intriguing and they can explain, things that we don't know exactly why they happen at the micro and nano scale. With that, I thank you very much. I acknowledge the financial support from CAUS, and I'm open for questions if you have. Thank you very much.